Yes, hello everyone. Yeah, so just an overview of where we are. This will be my third talk. First talk I gave you this sort of big picture of what's going on in this mini course, of what's going on in this project with Mikolaj. First talk, 0 definitions, 0 proofs. Second talk, all definitions, 0 proofs. Third talk, 0 definitions, all proofs. So yeah, I start with a disclaimer, an apology. Today I'm going to go very, very fast, but I am happy to talk about this at length. You know, my approach to mathematics, Grothendieck had this metaphor about opening an avocado, right? I'm a millennial, so I can't afford avocado. But you know, I have working class roots. As some of you know, I worked as a baker. I would compare mathematics more to making bread. But I'll maybe say something about this later. Yeah, so here is the theorem, and this is the theorem that I will prove today. So I won't repeat the statement. It's the same statement as yesterday. I've added the definition of the notion of Faber. I will remind you of this notion when the time is right. And then we have theorem B, which is similar to the theorem before, except now what I claim is that the cost of this Poisson action on G times the IPVT has cost 1. Okay, so I explained in the first lecture why the thing on the right-hand side is actually, why this thing is actually 1. And then today I will connect rank gradient to this cost. Okay? And it will go through this result, which is cost monotonicity. And I have this slightly mysterious attribution here because I'm, in all honesty, not sure who the correct person is to attribute this to. So I would say it's some combination of Kekris and Mikolaj Fraczyk. But one thing that I can say for certain is that the locally compact case, this was me. It's in my paper with Mikolaj. So this is the key tool that we're going to prove. And then you will see how I apply it to prove these two theorems. Okay? Or, well, one step of the proof of the second one. So what does this theorem state? So the setting is that we're looking at some finitely generated group. And then we're going to take a sequence of invariant random colorings. So I spoke a lot about these yesterday. And our assumption is that this sequence of colorings weakly converges. Okay, so I'll remind you of weak convergence momentarily. But what is the conclusion? The conclusion is that the lim sup of the cost of this sequence is at most the cost of the limit. Okay, so this is some sort of semi-continuity result for the cost function in the space of actions. And this is what I'm going to prove. Okay, and maybe you can start to piece together how these theorems are actually proved. I said that the cost for some particular invariant random colorings is essentially the normalized rank. And so maybe you start to see where this is going. OK, so I promise no definitions, but this is more review than anything else. So weak convergence. OK, this is the key concept for this lecture. So I may as well remind you of what it is. And I want to explain how I think of it as a probabilist, or whatever I am. So I say that mu_n weakly converges to mu, and this is now all taking place in this space of invariant random colorings. What does this mean? It's a series of finitary statements. Okay, so for all f inside of gamma, you think of f as a kind of window. And for all finitary configurations alpha, so this is in 0, 1 to the f. And for all epsilon greater than 0, this is some kind of tolerance parameter. The statement is that the measure of the set of configurations such that you're epsilon close to this alpha inside of this window, this should converge as n tends to infinity to that of the limit. Okay, so I'm not precisely denoting, precisely explaining what I mean here, but it will be kind of clear by saying these two things are epsilon close. And so sort of the slogan is, in any finite window, the statistical behavior converges. Okay. So some of you, I'm sure, are quite aware of what weak convergence means in the functional analytic sense. Something about integrating sequences of continuous functions or something like this. This to me always seemed like a hopelessly abstract way of thinking about these things. This is a very concrete space. Okay? This is a very concrete sequence of questions. It says, when I look in some finite window, the behavior converges. And I mean, if I would replace this with a slightly simpler space, I mean, those are really just like random vectors, and it's pointwise convergence. Okay? So that's the notion of weak convergence. And I want to give you a simple example. Okay? So here is the example. And the point of the example is to show that if you just naively apply this cost monotonicity with what I've presented to you so far, you will get nothing. So I want you to note that there is a natural inclusion of the configuration space, which I remind you was just the space of subsets of this group, inside of the space of colorings. Oop. Okay, natural inclusion. Okay, so what is the example? The example is, I want you to suppose that pi n is a sequence of point processes, okay, invariant point processes, but I'll drop the word invariant, with intensity going to 0. And so what I want you to check is the very intuitive statement. I mean, this is a sequence of point processes that are getting sparser and sparser somehow. Okay, and what I want you to check is that these guys actually weakly converge to the empty process. Okay? And I'll give you an example. The relevant example is if we take a sequence of finite index subgroups with index tending to infinity, this is something which will be implied by the Faber condition. This index, this is something I explained yesterday, is 1 over the intensity of the corresponding sequence of lattice shifts. Okay? So if the index tends to infinity, that's true if and only if the intensity of this sequence of lattice shifts goes to 0. So therefore, according to this little computation I encourage you to do, you get that then a random coset, a randomly chosen coset of gamma n weakly converges to the empty process. Okay. So now let's try to naively apply the cost monotonicity theorem before we've even proved it, just so we see that it's really a useful tool. Cost monotonicity application. Okay, so I'm going to take gamma n inside of gamma as above. And then we know what the cost of these guys is. And we know that they weakly converge. So you plug it into the theorem. and you get a very dramatic result. Cost of the lattice shift action minus 1. We have seen what this cost is. This is the normalized rank. Whoops. Lim suit. Okay, the theorem tells us that this converges to the cost of the limit, which is gamma acting on the empty process, minus 1, which is the rank of gamma, minus 1. Okay, so it appears that the theorem is useless. And I want to reassure you that the only thing which is wrong here is in how we've chosen to apply it. Okay, so there is an alternative construction that I'll explain at the end.
Calling it the lattice shift action because we're supposed to think of it as G maximum, G mod.
Yeah. I mean, for simplicity, I switched to the countable setting. So, I mean, these are just finite index subgroups. I mean, it's not wrong to call them lattices, right?
But are these, what is supposed to happen on the right in that?
The replacement here? Yeah, that would be a bit mysterious, right? I mean, the answer is that you don't do this. I mean, we've already seen that it's useless in the countable setting, so yeah. Yeah, this is something that Koki Takamoto pointed out to me yesterday, that this is a slightly strange computation, but I mean, the point is it doesn't work. Okay, so yeah, now I'm just going to do a quick little trick. So I'm sorry for that. I like invariant random colorings with the unit interval, but it will be more convenient for topological reasons if I replace this by a slightly different space, the Cantor space. Okay, so my apologies. The notation will be slightly inconsistent, but I hope you can follow along. So the unit interval, as we all know, is isomorphic to the Cantor set. And this one's my favorite Cantor set. And sorry? As sets and with a natural measure that I'm about to introduce. Yeah. So yeah, it will be convenient for me to replace the unit interval by this Cantor set, essentially for topological reasons. Okay. There is genuinely something subtle going on here, but I'll try to sneak it past you. So I want you to equip kappa with the natural measure with nu being just independent coin flips. Okay, so the product measure, you could write it down if you want. And as I said, this extends to an isomorphism of measure spaces, of the interval with Lebesgue measure, and the Cantor set with nu. And this also, in turn, induces an isomorphism of the Bernoulli shift action where I'm just changing what's going on in each coordinate. Okay. So this thing is what I'll probably start denoting by blackboard M. Okay. So now I want you to recall the definition of cost, because we're going to prove this cost monotonicity result. So recall that the cost of some point process pi, I gave you two formulas, and I'm going to use the other one. So this was the infimum over all graphings, or connected factor graphs. of the average degree, but you compute it for this lift, this extension. Okay. G tilde was this extension that I explained. And so now what I'm going to explain is that there is a different way that you can understand this cost. And this is something that Mikolaj and Nick Nikolov did, where you understand this cost as actually being a groupoid cost. Okay, so it pains me to say this word, but I tried very, very hard. I cannot get the groupoid out of this proof. So yeah, sorry for that. I'm going to introduce a groupoid. So M0, this will be the set of configurations that contain the root. Okay? And yeah, I also warn you that I'm trying to make the translation from the non-discrete setting to the countable setting, and I left this quite late. So it is possible there are slight errors with my formulas. But if you understand sort of the music, that would be nice. So these are what I call rooted configurations, because they contain the root, this element 0. Okay, so it turns out that this is the unit space of some groupoid, and this is what I'll define now. So what is the groupoid? So I have M0 with an arrow on top. This consists of pairs of a rooted configuration and some element in it. Okay, so this is a pair, a rooted configuration, and an element of gamma, such that this element is in the rooted configuration. Okay, I'll refer to this as the arrow space. And this is a groupoid. Okay, and I'm not going to spell this out because I think you guys are at least somewhat comfortable with groupoids. If you're perturbed, then let's figure it out in the exercise sessions. So the picture in my head is the following. So I'm looking at a rooted configuration. That's some subset which contains this root. And then I've marked one of its additional points, this G. And I'm thinking about it as an arrow, like this. Okay? And if you put a whole bunch of these pictures together, you end up with a factor graph. So that's what I'm going to explain next. And yeah, I mean, if I had some other element H, I could think about an arrow like this. And then there would be a natural way to compose these, and that would give me this arrow. Okay? So I encourage you to come to the exercise sessions and figure this out if you're interested. Otherwise, just take it on faith. So there is a multiplication operation on this space of arrows. And the bummer is that it's only partially defined. That's what makes it a groupoid, right? A groupoid, you can think of it two different ways. It's something that behaves like a group, except the multiplication operation is only partially defined. Or it's a category where every arrow is invertible. Or it's a whole bunch of arrows that you can multiply together. Okay? So okay. So this is the groupoid, and I promise it will be useful somehow. I want to understand subsets of this groupoid. And these are exactly the same thing as factor graphs. So I'm setting up a correspondence, and that's what I'm going to do now. So G here should be some factor graph. Okay, it doesn't have to be a graphing. It doesn't have to be connected. And you'll recall that that was a map from the configuration space into this space of graphs. And now I can associate to this some collection of arrows, which I'll denote by script A sub G. And this is just, I look at all arrows, which, well, all the arrows that appear. all the arrows that appear as rooted configurations. Whoops. Such that 0, G is in G of omega. Okay? So this is some association of a set of arrows to the factor graph, and there is an inverse to this. So I'll write this down. Given now some other set of arrows, you can build a factor graph associated to it, which I'll denote G sub A. So G sub A of omega is supposed to be all pairs G, H in omega times omega, such that if I look at this slightly strange expression, omega G inverse H, this is an element of A. Okay. So I encourage you to sit down and do the elementary calculation to check that these are actually mutually inverse operations. And that means that we have constructed a correspondence. Okay, so there is a correspondence between factor graphs G. These are in one-to-one correspondence with subsets. A of the arrow space. Okay, if you want to be pedantic, I mean measurable factor graphs and measurable subsets. And you might ask, well, what about the graphings? What do they correspond to? And they correspond to something very nice. So inside of here, we had the set of graphings. These were the factor graphs which were connected. I guess it's a proper inclusion, but anyway, who cares? Whoops, this was supposed to be one-to-one, one-to-one. I think I saw this once in some algebraic geometry course. These are in one-to-one correspondence with generators of the groupoid. Okay, if I look at what this collection of arrows generates, it's the whole groupoid. Okay, so I didn't define what this expression is, but I hope you can figure it out. I mean, you just multiply all pairs of arrows going both ways, all finite products like this. Okay. And our groupoid was not just, well, we wanted to take average degree of these graphings. So what does this correspond to in the groupoid language? So the average degree of, well, not necessarily a graphing, maybe just a factor graph. This can be expressed in a slightly strange expression. So mu0 with an arrow on top of the corresponding subset AG. Where AG is as above, so below. Where mu0 for some subset A, this was this expectation. This thing that I was saying is secretly something called palm measure in disguise, or maybe palm measure up to a fixed multiplicative constant. So I didn't have time to thoroughly check. Indicator that pi gamma is in A. Okay, here mu is the law of pi. Okay, what's all this about? I should summarize this. So we really don't need very much of this groupoid, just some basic fact. So all we need all we need is that if I look at this object, the space of arrows, together with this special measure that I've just defined, this is what's called a PMP groupoid. Okay, I won't define this term PMP, but it was the integral equation I wrote on the board yesterday. And in this language, we can now express cost. And this is what I was trying to avoid, but it is what it is. So the cost is equal to the infimum over now subsets A of the corresponding arrow measure, where I look at all generators. So what A generates is the entire thing. So this is groupoid cost. Right? Makes sense. The rank was the minimum size of a generating set. So what should be the rank, the cost of a groupoid? It's the minimum size of a generating set. Right? So this is groupoid cost, and this was formally introduced by Arbet Nikolov. And this generalizes the cost of Gaboriau. Okay, so for when your point process happens to be what's called essentially free, so it has no symmetries, these are the same notion. Okay, so Gaboriau gets all the credit, but I mean, formally it was those two that introduced it. Are there any questions at this point? Or no? How's your day? OK. Wow. Cold. OK. OK, so yeah, I said that this is not just a groupoid. This is a groupoid with a topology, right? Not just any old groupoid from the gutter, but this fellow went to the high street. So note that M0, this arrow groupoid, I mean, formally, it's some subset of this space, which certainly has a topology, times gamma. So this has a topology, just the subspace topology of this product. And even nicer, and this is what we're going to use, it has a countable basis of Clopin sets. Okay. So this countable basis of Clopin sets, this will be important for us. Another thing that is important for us is that this groupoid is a nice space. Okay, this has no formal meaning, but it implies something. It implies that this arrow measure is a regular measure. So depending on your background, maybe you know or don't know this term. When I say a measure is regular, what I mean is that the measure of any set is the infimum of the measures of open sets that contain it. Okay? Any measure, any nice measure on a nice space has this property. OK, and so this tells us something. It says that when I'm looking at computing cost, I'm supposed to be looking at all of these generators. But actually, I can get away with just looking at open generators. This is just using the regularity property. So hence, the cost of this pi is equal to the infimum over all subsets of the arrow measure, such that A generates and is open. OK, I hope this is clear. Yeah, I promise no definitions, but I'm a liar. Definition So I say that a collection of arrows is continuous for this measure, for the arrow measure, if, well, whenever you have mu n weakly converging to mu, you get the corresponding convergence for the sequence of arrow measures. Okay, so the notation gets a little cramped. I'm sorry about that. This is another reason why it's better to write things in terms of probability. But anyway. Okay, and here is the key example, the only example that we need. And this is something for you to check. Any Clopin subset of this space. Okay. This is almost immediate from the definitions. So now, let me give you the key lemma, and you'll see that cost monotonicity follows almost immediately from it. So here is that lemma. If gamma is finitely generated, then any open generator A contains a Clopin generator. C. Okay. This will be quite an easy lemma to prove. And then this gives us the proof of cost monotonicity. So let me just spell that out. So proof cost monotonicity okay, when I say cost monotonicity, I mean what's on this other board. Okay, so given epsilon greater than 0, I want you to choose an open generator which is close to computing the cost of the limit. Okay, such that the arrow measure of this guy is at most the cost of mu plus epsilon. Now, take C as in the above lemma. And now we have a very short computation. So if I were to try to compute the cost of mu n using this C, I mean, C is a generator, right? So by definition, I can plug it in. And I get that this is, at most, the arrow measure of this C. Right, C generates. But if you believe in the example, these Clopin subsets, they have this continuity property. And so if I apply this, I get that this converges to the measure of the limit. Okay. And now we all remember that measures are monotone functions. Yeah, that one doesn't even need an explanation. And that was, what was it? Cost mu plus epsilon. So that's the proof of cost monotonicity conditional upon the claim. And as you see, it's very straightforward, right? There's not really much going on there. It's slick, but you know. And now you imagine that this lemma is where I'm going to have to roll my sleeves up. That's why I've been cuffing them this whole time. Yeah, this one is way worse than the other. So apologies to all the ASMR people out there in YouTube. Okay. Yeah, you can probably see that the proof is this long, so it can't be too bad. So proof of lemma. So as I explained, this space has a countable basis of Clopin sets. Okay? And I'm supposed to be taking any open generator and finding a Clopin generator inside of it. Okay, so it seems like the right thing to do would be to write this open generator A as some union of CNs, where CN is an open. Well, it's just an open Clopin subset at this point, right? Okay. And so the claim is that if you crop this at some point, you end up with an actual generator. So it's always Clopin because it's a finite union of Clopin sets, right? So the only part of the claim is that this is really a generator. Okay, this is the most mysterious part of the proof. And so what you can check is that, OK, this is a topological groupoid. And so we're looking at open sets. If you start multiplying open sets, you also end up with open sets and so on. So you can check that if I look at just finitely many of these guys and what it generates, then this is open. And moreover, I mean, this is increasing to what A generates. But A is a generator, so that's the whole thing. All the arrows. Right? If you give me some element in what A generates, I can express it as a finite product of arrows in A. And so, you know, eventually it's going to be in one of these guys. Oop. OK, now compactness comes in. This is what I say when I say this proof is mysterious. I want you to note that M0 times S, where what is S? S is, as usual, my finite generating set. This is a compact generator. I mean, if I'm looking at this cropped thing and what it generates, it's increasing to the whole space. So at some point, it has to contain this guy. So hence, there exists n such that if I crop it at the nth level, this contains this compact generator. So seems to me that this guy is the desired Clopin generator. Okay. Are there any questions about this proof? Okay, so now we have the cost monotonicity result. And what we saw, what was on this board previously, is that if you just naively try to apply it, you get nothing. And now I want to tell you the fix. Okay? So this is the application. The only time I'm going to use this Faber condition. So recall that gamma n in gamma is Faber if for all identity neighborhoods, all finite identity neighborhoods, you have that the probability of this randomly chosen conjugate intersecting this set being anything other than just 0 tends to 0. Okay, so I have not particularly motivated this Faber condition or explained how to think about it. I mean, these conjugates, these are always stabilizers of something, right? This is like the stabilizer. Yeah. It's right in the notes. So, okay. Yeah. Yeah, so I mean, this conjugate is the stabilizer of something. It's the stabilizer of a point in the quotient. And so what this is saying is that sort of the U neighborhood of that point is fat. You can think about this in terms of saying the injectivity radius is large at most points of the quotient. Another key word is sophisticity. So it's saying that this corresponding sequence of quotients forms a Sophic approximation. As I said the other day, there's this famous paper, the Seven Samurai paper, where they show that this condition is essentially automatic. So.
By the way, A is there exists A such that that intersection is not 0.
This is a probability, so it's for most. Like this subgroup has finite index, so it has finitely many conjugates.
Okay, the set of A's that satisfies that.
The measure of the set of A's that satisfy it. Yeah, I write it as a probability. Okay. Right, so this is the Faber condition. And now finally, I'm going to connect this whole business of rank gradient and cost. So I am going to introduce another kind of invariant random coloring, which I don't have a good name for it, and so I'll call it coset-wise Bernoulli processes. And yeah, I don't know how to describe the thing that I'm about to do now, but I'll call it the trick. And I want to attach my name to this. Okay. So I'm going to, we saw that if I had some finite index subgroup, I pick one coset of it. This is no good. This doesn't work for cost monotonicity. So I'm going to give you this alternative that I'll call coset-wise Bernoulli processes, and you'll see that they do the job for you. So the setting here is that I have a finite index subgroup. And I'm going to pick a transversal for this. I have no idea if that's a right transversal, left transversal. The condition that I want is that when you multiply it on the right, you get the entire group. Okay, so I want you to generate an invariant random coloring as follows. Okay, hopefully I have enough room. So this is the picture of my group. It's this potato. And I can pick one coset of lambda at random. Okay, so pick a lambda at random. But now we need to color it. Okay, so color it color it by what? Well, just a uniform 0, 1 random variable. Okay, size 0. So this is still no good, but I want you to color the remaining guys, which I guess are a lambda t, t and t, by something else, psi t, which is uniform 0, 1. And all these random variables should be independent. Okay? That's not enough room. Sorry. No. So this is some a lambda t. I mean, there's only finitely many of these guys, right? Okay, and I want to make some comments about this process. So the first one is somewhat disturbing. Oh, I didn't give it a name, but the notation should be clear. So note, I'll denote this process by pi sub lambda. Okay, so it's an invariant random coloring. And so what I want you to note is that this process is non-ergodic. That's slightly disturbing. It's non-ergodic. It's, well, I can describe it another way. It's a factor. So this was this term that I defined yesterday, a factor of the lattice shift. Oh. Yeah, I should write it with the action, I guess. Times the unit interval to the t, where here you act trivially. Okay, I think in the paper with Mikolaj, maybe I call this the dummy IID or the fake IID. I mean, this is some process that it sort of looks IID locally. If you're just looking at points that are in one coset, or points that are in different cosets, it looks like the IID. But if you take 2 points in the same coset, then it's emphatically it's not the IID, right? Okay. One more point. So what is the cost of this process? I don't know. But I can give you inequality. So the cost of the lattice shift, well, I mean, cost can only increase under factors. And cost respects ergodic decomposition. And this thing here, this is essentially the ergodic decomposition. Okay? So this is at most the cost of this coset-wise Bernoulli process. Oh, a bit too zealous. Okay, and as you recall, this is 1 plus the normalized rank. Okay, this is one process, but we wanted to take this for a Faber sequence. So what happens with the Faber sequence? So now take now take gamma n in gamma to be Faber. And what I want you to check that this corresponding sequence of coset-wise Bernoulli processes, in the limit, gives you the genuine Bernoulli. So if I look at pi gamma n, what I claim is that this weakly converges to the Bernoulli. And so now, if you plug this in to the cost monotonicity thing, you get theorem A, or theorem A prime, right? So why is this true? I have no idea if me saying anything is actually going to be useful here. But I mean, the picture should be quite clear. I mean, the Faber condition, I mean, what's going on here? If I remember, weak convergence was something about like the statistical behavior in finite windows. So here's my gamma. If I'm looking at this pi lambda, so it's a random coloring of gamma, and I observe it in some finite window, this window intersects the cosets of the randomly chosen coset, that's a lambda. And it intersects it in some sort of way. So this is maybe a lambda, this is maybe a lambda t1, et cetera, et cetera. Okay? And what the Faber condition is telling you is that in this picture, what you're seeing most of the time is not something like this where each one of these intersections has multiple points in it. The Faber condition tells you that you just see one most of the time. I mean, most of the time you see nothing, but at most one. Okay? So this process, it looks the same as the Bernoulli process, as long as some condition, as long as for all t, the what was it? Gamma n. A gamma n t intersect w has at most one point. Okay. So this was the one-line condition, one-line calculation that I promised. So apply Faber condition with u being it's either w inverse or w inverse w or w inverse. So I mean, check when. Suppose this happens. Okay, so suppose suppose I have one of these bad cosets, right? So that means that I have two elements u1 and u2, which are in U and distinct, that can be written in this form. So u1 is a gamma 1 a inverse, and u2 is a gamma 2 a inverse. And now I do a very sophisticated multiplication. Let's check what u1 u2 inverse looks like. So that's this thing. And so you get some kind of cancellation. What do we get? A gamma 1, gamma 2 inverse, a inverse. And so now this thing is in w inverse. And this thing is in a gamma and a inverse. So this proves weak convergence. Okay. Okay. So in the remaining no minutes, 5. Wow. Okay. Plus epsilon. Does the 5 include questions? What? Does the 5 include questions?
That's an innovation of Anton and Simeon's. They're surprisingly good questions. I'll ask you because they good questions this week.
OK, I mean, I just wanted to say something briefly about this cost-monotonicity result and how it connects to theorem B prime. So theorem B prime. What do I mean by theorem B prime? This fact, this is something that that will be presented tomorrow, I imagine. And then the one thing that's missing is, I mean, why does this connect to fixed price? Hence, this is, if you add in this cost monotonicity, you get fixed price 1. OK? I mean, what is proved here is that this one particular action has cost 1. But fixed price, you have to prove something about all actions. So why is this connected at all? And the point is that because this object, this IPVT, is what's called a weak factor of IID, by cost monotonicity, it doesn't change the cost. So this guy has maximal cost. The Poisson has maximal cost. This is what I proved with Mikolaj. But this is a theorem I don't know how to apply directly in literally any case. You have to apply cost monotonicity again and get some other action that you can actually get your hands on. And that's this, this product, G times the IPVT. And so, do we even want to write all this? Yeah, I mean, this is going to be real sketchy. But I mean, so yesterday, I finished by constructing the Poisson point process as a factor of the Bernoulli shift of the lattice. OK? And I didn't say anything about the intensity. I mean, this construction works for all intensities. So you can think about that as I specified a family of maps which go from the Bernoulli shift of gamma into the configuration space of G. So for T here is just some real parameter. And the Bernoulli process here, or the Lebesgue measure, the power of the Lebesgue measure, this under this map takes you to the Poisson. The Poisson point process of intensity T. OK, and now I'm going to do a weird little trick. So this is something that if you're familiar with factor of IID constructions, it will sound familiar. So one thing I want you to note is that the Bernoulli shift is sort of self-similar. So 0, 1 to the gamma, Lebesgue to the gamma. This is isomorphic to gamma acting on, well, the product of this with itself. Crossing boundaries. OK? This is just because the unit interval is isomorphic to the unit square. Right? There's not really much going on here. And what we do in the paper, which I don't really have time to get into, is that, I mean, if I think about this as being two independent samples of the Bernoulli shift, then I could look at applying this map to one of them with a fixed parameter, and this map applied to the other one with the parameter decreasing.
What do you mean by isomorphism?
Like isomorphism as PMP systems.
So it's not always true?
Well, that would be troubling.
I mean, if you're talking about Poisson point, not the sequence, then?
I mean, this is the Bernoulli shift, no?
Bernoulli shift depends on entropy.
These all have infinite entropy. It's all the same. I mean, it's the explicit map that you can write down. So if I apply this family of maps where one of the parameters stays fixed and the other one is varying, then I get a sequence of maps into some space. So this is the configuration space on G times the configuration space on G. So it looks like I'm not doing anything, but I don't want to apply this for phi t on the nose, but I want to apply this for some strange normalization. In the paper, it's written eta t, so phi sub t. And now this will take values in a slightly different space. D is the space of shifted distance functions. Okay, so D consists of all of these distant functions. So these are supposed to be continuous functions. So S is some parameter, X is in G. Okay. This hat here, this refers to the usual embedding that you have of a metric space into its metric dual, the space of continuous functions on it. Okay, and this is the space where Mikolaj computes the limit. And what he ends up with in the limit is some Poisson point process on this space, which turns out to be concentrated on like the homogeneous space, this G mod U. And if you plug all this in to the cosmonoticity and you use the actual, the upgraded version that I had to do with Mikolaj, what you end up with, okay, so sorry, this was all very fast. What you end up with is that the cost of the Bernoulli shift is at most the cost of the Poisson on G times, and after you do this identification, you can really think about it as the Poisson on G mod U. Okay, and so this thing, we know the rank gradient is controlled by this thing, and so if you show that this thing is 1, which is what you'll see tomorrow, hopefully, then you get this whole vanishing of rank gradient. Okay, and so yeah, I'm very much out of time. The only thing that I would like to say is I encourage you to think about, I mean, what on earth is going on with this argument? I give you some cheap graph for this thing, and I promise you, through all of this abstract machinery, this corresponds to some very cheap generating set for a deep lattice. What does that look like? I have no idea, but it works, right? So that's the whole proof. So I'll finish there.
Questions?
Are there any proof that rank gradient is simple by cost?
Yeah. So when I said that that there are technical distinctions between the two theorems, what he shows is that if you have a Faber sequence of lattices and you take the ultra product of those as actions, then you get that the rank gradient is at most the cost minus 1 for that mysterious ultra product. But there weren't any examples where you could compute this or estimate it. And what we do is we say, okay, well, this Poisson point process has maximal cost. So like in the general LCSC setting, I do something like this trick, and I get that the rank gradient is controlled by the limit of some IID-labeled process. I don't exactly know what it is, but it's some IID-labeled process. And just like what I explained with how you get from the Bernoulli shift to the Poisson point process, you can get from any IID-labeled process to the Poisson point process. And so it chains together through that. But it's not any more explicit. If you wanted to make this proof like explicit or effective or something like this, you would need to start looking at the Poisson Voronoi tessellation of the corresponding sequence of quotient manifolds and prove things about like its expected degree. But I think this is quite difficult.
Okay, any other questions? Okay, not let's thanks again.